In the previous videos we discussed the 3-5 absorber materials and their use in multi-junction devices. We will now look at some special applications of the 3-5 solar cells, starting with concentrator PV. In this video we will focus entirely on the optics of the lenses used for concentrating light. The learning objectives for this video are to recap Snell's law of refraction that was first introduced in the PV1X photovoltaic energy conversion course. We will then look at some refractive lenses and the Fresnel lens in particular. Finally, we'll look at some reflective mirrors that can also be used for concentrating photovoltaic applications. Let's first look at the Snell's law of refraction. This law states that the angle of transmission depends on the angle of incidence and refractive indices of both materials. It also states that the ratio of the sinus of the angles of incidence and transmission is equal to the ratio of the refractive indices of the media. Increasing the difference between the refractive indices will increase the angle at which the light beam is refracted. The angle of reflection, however, simply equals the angle of incidence regardless of the refractive indices of the two media. So let's put Snell's law into practice. We will follow a number of beams emitted from the blue point source here. The point source is inside a medium with a refractive index of 1.5, for example glass, and the light is emitted into a medium with a refractive index of 1, such as air. The first beam arrives at the interface under normal incidence. According to Snell's law, this beam is transmitted under normal incidence as well. At an angle of incidence of around 20 degrees, the beam is refracted at an angle of 30.9 degrees. A refraction of the intensity of the beam is reflected. A beam with an angle of incidence of 35 degrees is refracted at an angle of 59.4 degrees. This shows that as the angle of incidence increases, the angle of refraction increases even more strongly. When the light beam is incident under an angle of 41.8 degrees, the beam will propagate perpendicular to the plane of incidence. This angle of incidence for these particular refractive indices is known as the critical angle. If the direction of the beam is reversed, the beam will travel the same path. This reversibility means that a flat material will not focus any light. If we take, for example, this flat surface with a refractive index of 1.7 and a finite thickness, light incident under an angle of 40 degrees will be refracted at an angle of 22 degrees. At the second interface, the beam will again be refracted back to an angle of 40 degrees. The beam therefore only undergoes a horizontal shift. For that reason, concentrator lenses are spherical. The shown lens is a spherical on one side. The spherical lens is designed such that the perpendicularly incident light is focused onto a focal point at some distance from the lens. In reality, a lens has some optical aberrations. This means that not all perpendicular incident light will be concentrated into a single focal point. For instance, any spherical lens will have spherical aberrations. The rays incident closer to the top and the bottom of the lens end up converging at a shortened distance from the lens. The refractive index of a material is wavelength dependent as well. Generally speaking, the refractive index of the types of glass used for lenses decreases with increasing wavelength. For short wavelength blue light, the glass will therefore have a larger refractive index mismatch with air than red light. This means that blue light will be refracted more and have a focal point closer to the lens. This is known as a chromatic aberration. These optical aberrations pose some serious challenges for lenses in imaging devices, such as cameras and beamers, where a concentrated focal point is essential for creating a sharp image. For concentrator PV, the light needs to be focused onto a solar cell with a certain area. Even though the optical aberrations have to be considered during the lens design, the lenses used for CPV have a much larger tolerance. As we can see, This lens is designed such that all perpendicularly incident light is focused onto a solar cell. This has two important implications. Under normal incidence, both direct and diffuse light will be incident on the lens. The diffuse light will be incident from all angles. For most of the angles, the light will not be refracted onto the solar cell. CPV therefore only makes use of the direct light. Most of the diffuse light is not used. The second implication is that the lens and the solar cell have to face the sun. Otherwise, the sun's radiation will not be perpendicular incident. This means that CPV requires a tracking system that adjusts the direction of the CPV system during the day. We will discuss the tracking system in more detail in the next video. For CPV application, normal lenses would have to be very thick. These lenses would be relatively expensive and have a relatively high optical absorption. Therefore, Fresnel lenses are generally used. For Fresnel lenses, the lens is collapsed back to zero thickness at a number of points. This figure illustrates how this is achieved. The lens is divided into a number of grooves. The red areas basically represent excess material which is removed. The resulting Fresnel lens has the same curvature but is much thinner, resulting in negligible absorption losses. Since the Fresnel lens can also be used to disperse a concentrated source of light, one of the most successful applications is the one in lighthouses. An alternative to refractive lenses is the use of refractive lenses or mirrors. A reflective surface with a parabolic shape will focus the rays at some distance parallel to the parabola's axis. To that end, large parabolic dishes, such as in this picture, can be used. Alternatively, parabolic throws can be used like this one. Please note that this picture shows a solar thermal system, but the same principle applies to CPV. In summary, we discussed Snell's law of refraction, applied it to see how spherical lenses concentrate light onto a focal point. We discussed the spherical and chromatic aberrations that occur for lenses in reality and how lenses only concentrate direct light and therefore require solar tracking. Finally, we discussed Fresnel lens and the use of mirrors for PV systems. In the next video, we will discuss the effect of light concentration on solar cells.